now we will be discussing another important concept of circuits elements, which is the resistance and also connected with it the resistivity of materials. And we start again with some conductor and with the microscopic equation for the current flowing in this conductor. So it's a cylindrical conductor and a circular cross section, and there is an electric field applied, and so there is a current I flowing in this conductors. Okay. Now we take a portion of this conductor and we assume that this has been connected to a battery or so. So the electric field has been set in this conductor, and so there, whenever you have an electric field, then there is a potential difference across the two ends of this conductor. So this is point A, this is point B. So there is delta V, which is set here across the two ends of the conductor. Now the current density is just what we have defined, is this expression. Now it's quite reasonable to assume that the current density in a conductor is actually proportional to the electric field that has been applied in that conductor. Well, how to understand this or how to swallow this? The reason is very simple, because what causes the charges to, because this is your current, okay? Now you cannot change Q, you cannot change A, you cannot change N. These are given for a material here or here also, okay? You cannot change these two. For a given conductor, these are given. The only thing that changes, you can change VD, and this changes why? Because of the electric field that you are applying in a way. And therefore, it makes sense to assume that the current density that is generated, and so the current also, is proportional to the electric field that you have applied, okay? This is a general expression. This is a general expression, valid for any material and not necessarily for conductors. We say that, we think of it in this way, we say that, okay, your electric field is the trigger, you apply electric field to the material. J, the material responds by having a current generated there. What determines how much current will be generated is what? Is sigma. This quantity, sigma, is generally a function. Okay, it's a variable quantity depending upon how much E you have. Okay, and this is called the conductivity of the material. Now, for parts, if you are talking about a conductor, then for almost all conductors, this sigma is constant for any electric field. In other words, it doesn't change by changing your electric field. So it's just a constant, independent of the electric field. It can depend on temperature only. And therefore, the relation between the current generated when you apply a given potential difference or a given electric field, and so potential difference, is actually constant. Okay, the proportionality constant here, sigma, that is constant of proportionality. Okay, so it's the proportionality constant. It doesn't depend on E. Now, so this is what I'm saying here. Okay, for many materials, this quantity sigma is constant, and so J that is generated by an electric field is directly proportional to this electric field because sigma is constant. And this sigma is called, in general, it's called the conductivity. And when it is constant, then we say that this relation becomes Ohm's law. So Ohm's law says that for some materials, the ratio of the current density to the electric field is constant sigma. And this is independent of the electric field producing the current. Okay, it is this. So Ohm's law says that J and E are directly proportional. The proportionality constant in this case is sigma. Now this is a relation applying to some materials, including almost all conductors. Okay. So this is Ohm's law. This is the microscopic version of Ohm's law. Well, most of you, if not all of you, have heard about Ohm's law somehow before, but it is not this version of Ohm's law that you have heard of, but actually the microscopic version of Ohm's law is this. It's a relation between the electric field applied and the current density that is generated, and saying that the generated current is directly proportional to the electric field, with a constant proportionality, being the conductivity of the conductor. And this quantity changes only with temperature. It doesn't depend on the electric field if the material is ohmic. Now, so this is an ohmic material, is a material for which this holds. A non-ohmic materials are materials for which doesn't hold. In other words, sigma varies with the electric field. Different electric fields will have different sigma, so it's not a constant. It's not a fundamental law of nature like Newton's law. Okay, Newton's law, it has universal validity. It's valid for any force and particle which has a mass. But Ohm's law, no, it's just an empirical relation valid for some materials, which are mainly the conductors. Now, we are familiar with Ohm's law in terms of resistance, and then we will move to define the resistance. Now, when you want to move to define the resistance, we start talking actually in terms of the potential delta V rather than the electric field. And this is the common practice in all practical applications. Nobody talks about the electric field generated in a device. You say the potential generated across the device. But of course, now you know that this potential is generated because there was electric field in that device. Okay, so I mean, talking about the potential difference is actually talking about the electric field, but it's easier and more practical. Especially, this is the quantity that we measure. We measure the potential difference, and this is the quantity that related directly to energy. And therefore, it is more convenient when it comes to circuits and electric currents and electric circuits to talk in terms of potential. And therefore, we start talking in terms of potential. But the potential, what's the potential across this conductor? Delta V is just E times L, the electric field times L. And therefore, Ohm's law, expressed in terms of potential, this Ohm's law, if you write E in terms of the potential, okay, E will be delta V over L. So if you write it in this way, this will be Ohm's law, assuming now that sigma is constant. Okay, so you have this. Now, if you write instead of J, you write it as I over A, then you get this relation saying that delta V is equal L divided by sigma A multiplied by I. Now, for ohmic materials, L and A, of course, for this conductor, they are constant because the conductor, I'm assuming the conductor is uniform. Okay, it has a given length and it has a given cross section. And since sigma for ohmic material is constant, then the whole thing is constant. This whole thing, this constant, which is L divided by A multiplied by sigma, we call it the resistance of the conductor. The resistance of the conductor. And you see, we are defining it for a uniform conductor because the cross-sectional area is uniform in this case. And so Ohm's law, and we call this expression, we call it the resistance of the conductor. So this is the resistance of a conductor which has a cross-section area A and length L. And so we have now Ohm's law written as delta V equals R times I, where R is a constant for ohmic materials, of course. And this is the more conventional form of Ohm's law that you are familiar with. If you like, we can call this the macroscopic version of Ohm's law or the practical version of Ohm's law. So it says that the current is proportional to the potential, the proportionality constant in this case, which is independent of the applied potential or the applied voltage, as we usually use in engineering applications, is actually the resistance of the material. Okay, and we can write it this way. Now, why is this actually a resistance can be demonstrated if you just write it the other way. You say that you take I to the other side, this becomes delta V over R equals I. So the greater is R, the smaller is I in this case. Okay, and therefore this is why it is a resistance, because as it gets bigger, it makes the current generated by a given potential smaller. This is why it's called a resistance. Okay, it's like the mass in Newton's law. The larger the mass, the smaller the acceleration you get from a given force. So the mass is also an inertia, or it's a resistance, an inertial mass. So here, this is why we call it a resistance, actually, in this case. Now, this relation is valid actually also for non-ohmic conductor. I mean, the resistance of any circuit element at any potential is the potential divided by the current at that instant. But in that case, this R will not be constant. I mean, when you divide, when you have applied different potentials across that circuit element and divide them by the generated current, for different potential and current combination, you get different value of R. Okay, it's not a constant. But the definition of the resistance of that conductor, of that circuit element at that potential and current is still this. Okay, so this is a point that is important to keep in mind also. Now, the resistance has units of ohm, as everybody knows, and we write it as this is the symbol for it, and the ohm is volts per ampere, as you know. Now, another quantity that is important and which usually used more than the conductivity is the resistivity, which is the inverse of the conductivity. So its rho is equal 1 over sigma. And if you do this, then the resistance in this case can be expressed in terms of the resistivity rather than the conductivity. Now, we had R equals L over sigma A. Now, with rho being 1 over sigma, then we have just R equal rho times L over A. So this is the expression of the resistance of a given conductor with length L and a uniform, which has a uniform cross-sectional area A. Now, as you can see, what L and A are geometrical factors that depend upon the conductor, but rho here is a quantity which depends on the material. And for different materials have different rhos. It depends only, it varies only with temperature. So to sum up, every ohmic material has a characteristic resistivity that depends on the properties of the material and on temperature. It is just what, as I have said here, this quantity rho, okay, because this is independent of L and A. I mean, R depends on L and A and rho. These depend on the geometry, but this is independent of this. So it depends on what? Depends on the material. And I'm talking about an ohmic material. So these ohmic materials have resistivity, and this varies, depends on the type of material, and it varies with temperature only. We will discuss this. The resistance, on the other hand, is a characteristic of the object. So resistivity, while resistivity is a characteristic of the substance, of the material, this is characteristic of the conductor because it depends on the length and the cross-sectional area. Well, ideal conductors must have zero resistance, and ideal insulators usually must have infinite resistivity, but nothing is ideal. Now, graphically, if we have an ohmic device, then if you plot I versus delta V, then what you get is a straight line because the resistance is constant and the slope in this case will be I 1 over R. Okay. In engineering application, it's more common to plot I versus delta V, but sometimes, in physics especially, we plot actually I on the horizontal axis and delta V on the vertical axis. Okay. Actually, it's I is the independent variable and dV is the dependent variable because you change the voltage and the I is the response. Okay, but in engineering, it's more common to plot it this way. So in this case, the slope, however you plot it, the relation is linear for ohmic materials, and the slope is 1 over R, and the slope is 1 over R. As I said. If you have a non-ohmic material, like a diode, for example, then if you plot I delta V, then the relation between them is not linear in this case. Okay, so an example, as I mentioned, is just the diodes. Diodes are some circuit elements that are important in digital electronics, and their I versus delta V is not constant. As I mentioned before, at any instant you can find the resistance of the device at any point by finding delta V by delta I, but this quantity will not be constant Okay. Do this checkpoint before you proceed further. And also, this is an interesting checkpoint about non-ohmic devices. Now let's consider an example, a numerical example. So we have a 22 gauge nichrome wire. It has a radius of 0.32 millimeters. So now we know what 22 gauge means. It means 0.32 millimeters. And we are requested to find the resistance per unit wire, per unit length of this wire. Of course, we always we have tables where the resistivity is tabulated. So for nichrome here, for example, this is the resistivity of a nichrome wire. And we want to find what is the resistance per unit length. The cross-sectional area can be found from the radius. And so we want to find the resistance per unit length. So we divide it. And so the resistance per unit length becomes rho over A, because the resistance is rho over A times L. And you just substitute for A pi r square, and you do resistivity, the numerics, and you get for resistance per unit length is 3.1 ohm per meter. Now, if you apply a potential difference of 10 volts across this 1 meter length of this wire, what will be the current in this case? Well, the relation between the current and the resistance, delta I is equal delta V over R. Well, R is just R over L times L, so it's just, this value also, and so it's 3.2 amperes, 3.2 amperes, okay? So that's the current that will be passing through this wire. Now, as I mentioned, the resistivity varies with temperature, and for most conductors, it varies approximately linearly over a large range of temperatures. Okay, and this linear relation takes this form: rho equals rho naught times 1 plus alpha t minus t naught. Now we have to define what do we mean by each sample. Now the naught here, rho naught or t naught, refers to a reference point, and usually we take this reference point to be 25 degrees. So T naught is 25 degrees, which is the room temperature. Rho naught is the resistivity at that room temperature. Okay? So here say rho at any T is equal rho naught, it's the resistivity at room temperature multiplied by 1 plus alpha multiplied that temperature you want to find, the temperature, the resistivity at minus T naught. Okay? Now this quantity alpha is a quantity characteristic of the material. It varies from a material to a material, and it is called the temperature coefficient of resistivity. The temperature coefficient of resistivity, and it has units of degrees Celsius minus 1 in the SI system of units. So this is how rho varies with temperature, and as you can see, alpha is constant, so this relation is linear. This is true for a large range of temperatures, which is usually what you need in all practical applications. Okay, so this is how the resistivity varies with temperature. And if you want to solve this equation for alpha, you can write it this way: delta rho is rho minus rho naught, delta t is t minus 2 naught, so this is an expression for alpha. Now, the resistance, consequently, you just multiply this by L and divide by A, so you get all the way, and so you get the expression for the resistance. So it satisfies the same expression. So the resistance of a given conductor, which has a given cross-section, uniform cross-sectional area and a given length, varies with temperature also according to this expression. Now, the application of this is actually allows us to make precise temperature measurements through careful monitoring of resistance of a probe made from a particular material. In other words, by measuring if you know how does the resistance of a given probe change with temperature, then you can calibrate it, and so you get very sensitive thermometers. Okay, so this property of resistors can be used in some materials to design thermometers that measure temperature with high sensitivity. Now, before closing, we'll just outline the properties of two types of materials that we have not discussed before. Well, we just mentioned these quickly, but when we talked about, at the beginning of the course, we talked about conductors and insulators. Here, we mentioned semiconductors. Semiconductors are, materials between conductors and insulators. Now, what's striking about the semiconductors is that they exhibit a decrease in resistivity with an increase in temperature. Now, what we have seen is that as temperature increases for conductors, because of the alpha T minus T naught, the resistivity increases. Here, in semiconductors, however, there is a decrease in resistivity with the temperature increases. Alpha is negative. Okay? So this is an interesting property of semiconductors. And the reason for that is that at higher temperatures, the density of charge carriers in this case increases because of the properties of these semiconductors, of the microscopic properties of these semiconductors. This is what happens. Now, superconductors, on the other hand, are materials that resistance fall to virtually zero below a certain temperature. So if you look, for example, at this graph, you are plotting the resistance versus temperature here. How does the resistance change with temperature? So as you can see, this is in Kelvin, of course. And above 4.2, there is a linear relation between resistance and temperature. As usual, as temperature increases, the resistance increases. When you reach a point which is near 4.2 Kelvin, then in this case, the resistance drops virtually to zero. Okay? Now, these materials, this temperature below this happens, is called the critical temperatures, and the material in this regime becomes a superconductor. So it's a material which has zero resistance. And above that critical temperature, the material behaves like a normal conductor. When you cool it down until you reach that temperature, and it drops below that, it becomes a superconductor. So this is called the critical temperature. Of course, this is in this example, this is very low. Even in practical application, we are still the critical temperatures. We have designed discovered different types of superconductors, but the critical temperature is still well below zero, hundreds of degrees below zero. But it managed to find applications because of the vast amount of energy it saves, actually, in this case. Now, TC, of course, depends on these factors. And the important thing of one of the interesting characteristic of superconductor is that you set a current in that superconductor, then that current persists without any applied potential, because R is equal to zero. Then when you set a current there, then even if you drop the potential, the current persists because there is no material. Once the electrons are circulating, there is no resistance, so there is nothing to stop them. Applications of superconductors are actually the magnets, supermagnets, and in these supermagnets, the magnet is cooled down, usually in liquid helium, because only then you can reach these very low temperatures, below the critical temperature. And in this case, the magnetic field, because you are producing huge currents, the magnetic field produced about 10 times greater than a normal electromagnet, a huge electromagnet. And the major application, of course, is of high magnetic fields generated by electromagnet is in MRIs. The magnetic field there is sometimes the order of 3 Teslas, which is a huge magnetic field, and this is possible to achieve, under normal conditions, only when you have super conducting coils generating that magnetic field. try this check point before you proceed further. Now, I will close by considering quickly an example from the textbook. In this example, there is a certain light globe, that's light bulb, which has a tungsten filament. These are the old versions of these light bulbs. Now we have energy-saving light bulbs probably, but these on the old light bulbs we had a bulb, and there is it's evacuated from air, and there is a tungsten filament there. So the resistance of the filament is of this tungsten filament is 19 ohms at room temperature, about 20 degrees. Now, when the light is turned on, after some time, the filament reaches a steady temperature, and the resistance there is 140 ohms. It's measured to be 140 ohms. What is the operating temperature of the filament of the globe? In other words, what is the temperature of the filament when it reaches full steady temperature? It reaches its steady temperature. Okay. Now, well, immediately you have to start with this equation, and your target variable is t. You want to find t because r naught here is 19, r is 140, and t naught is 20. You want to find what is t. So at what temperature you will get this r, which is 14 ohms. So solve this equation for t. Everything now here is given. Alpha for tungsten, you can get it from the tables, and the temperature that you get is here is 1435 degrees Celsius. So this is the temperature of the tungsten filament in a standard light bulb, okay, which is quite high. And note that the resistance of that tungsten filament changes from 19 to 140 ohms. That's about 10 times when it is heated up, okay, which is a substantial change actually.